Thank you for the invitation. This is one of my favorite workshops. So far, we have very nice, two good talks, and I have there are a lot of talks that I don't want to miss. So thank you. So so I recently moved to PsiQuantum, but this is the work that I did while I was at Stanford. It's also related to some of the work that I did at IBM, and in particular, the one that I'm going to talk about is with Brian Singwell from University of Maryland. So as you know, there are lots of hypes about quantum computing these days. We don't know where this is going, but in the long run, we definitely want to do some form of error correction, which I think is why this workshop is so important. But as you know, the problem is that the noise. So right now, a lot of people have very high expectation about quantum computing in the near term. And I think for a lot of people outside of this community, they somehow think that the noise is not a huge problem. And I think they probably think this way because they're more equipped to the classical computer, in which the noise is, the primary source of noise is basically the cosmic ray that is coming from the sky. And as you know, I looked at the literature, and the noise rate, the noise of coming from that source is basically negligible. It's 10 to the minus 15 or some ridiculous number already in the 1990s. But in quantum computing, the best noise rate that we have so far is maybe 10 to the minus 3 or 10 to the minus 4, 10 to the minus 2, depending on the architecture. So that means that if your noise rate is 10 to the minus 2, probably after you apply 100 gates, something not good is going to come out. So of course we have a way to fix this problem, which is based on the theory of fault-tolerant quantum computation. The idea is that, of course, that instead of applying an actual physical gate to apply the gate that you want to perform, you have this encoded gate. And you basically concatenate these things many times. And so you basically concatenate these things many times, and that's how you get a fault-tolerant quantum computer. And there's this overhead, which is not bad, theoretically speaking. So if your target logical error rate is epsilon, the overhead scales polylogarithmically with 1 over epsilon. And of course, now we have much better schemes. There are these a constant overhead schemes, which I'm very excited about, and it looks like that's the step in the right direction. But for now, if we look at the best numbers that people have worked out in the literature, it usually goes like this. Of course, these numbers are really the range. It's not a unique number, but there was this very well-known paper by Austin Fowler and his friends back in 2012, wherein if you assume the raw physical error rate of, let's say, 10 to the minus 2 to 10 to the minus 3, and if your target error rate is 10 to the minus 10 to 10 to the minus 14, and if you use surface code-based architecture, which certainly has one of the better thresholds compared to other error correction schemes, you get at least, the overhead that you get is at least 100 to 1,000, and presumably higher if your error rate is 10 to the minus 2. And there are these alternative schemes in which you don't exactly have a planar architecture, using maybe 2D hyperbolic codes, and there are these more general LDPC codes. But generally speaking, there are some improvements, but the improvement is not huge. I mean, it's not we suddenly have an overhead that's on the order of 10, right? We still have these large overheads. So this is kind of a problem, at least for the near term, because even if you buy into this idea that the number of qubits are growing exponentially, well, first of all, your qubits have to be better. I mean, their quality, whenever people quote these numbers, the error rate that they have in mind is something 10 to the minus 3, and that is better than the best qubits that we have in the literature. So we have to make a better qubit, and we also need to increase the number by a huge amount. So this is a problem in the near term. So this is what motivated me to work on what I call as noise-resilient quantum circuits. And the idea is that maybe there is something, you shouldn't really expect to be able to do fault-tolerant quantum computation without doing any error correction, but maybe there is a very specific circuit that is good for something that has some unusual robustness to noise, okay? So formally, I define noise-resilient quantum circuits as follows. So as always, you have a family of quantum circuits with increasing size. But what's peculiar about this definition is that instead of the global state, what you care about is the expectation value of a select set of observables. So of course, you can define the set of observables that you care about to be the entire set of operators, but maybe you care about only like one local operators or like two local operators. So if the error of these things is like order epsilon, where epsilon is the physical error rate for all the circuit family, then I call this circuit as a noise-resilient quantum circuit. The non-trivial thing is that this quantum circuit, the depths might actually grow with n, and the main point of this talk is that there is a class of quantum circuits whose depth grows with n, but the error for the observables of interest does not grow with n. As I said, these are very specialized quantum circuits, but they do have this nice property of being more robust to noise. And for the purposes in this talk, I will say very briefly that they're useful for simulating currently intractable physical systems that people are having a difficult time studying. But if you have questions about this, you should ask me about this later. The main purpose of this talk is to explain the core ideas. And I want to emphasize that the core idea is very, very simple. And to show how simple it is, I would like to focus on a classical example and explain how this insight that you gain from the classical example can be generalized to the quantum case. So the plan is to first tell you about the classical toy example, and then I will show you the quantum analog, and I want to explain how we can somehow find an application of this quantum analog in a non-trivial setting. So the toy classical example that I have in mind is something that is called as the hidden Markov chain. So what's going on is that you have a Markov chain, but you have like a hidden node. So this here, like xt minus 1, xt plus 1, these are some like hidden variables that you don't observe. And from these hidden variables, you observe something that you actually get to see, which are like y's, okay? And the picture that you should have in mind is something like this. So you have this like hidden variable that goes around and interacts with a set of like observable variables sequentially. So it moves from like 1, 2, 3, 4, 5, and it interacts with like node 1, 2, 3, 4, 5 sequentially. And you get some probability distribution depending on like what kind of interaction you have. Now you can consider a noisy version of this thing. So let's say we have some physical process that describes the interaction between the hidden and the visible node. And now we want to replace that physical interaction by something else that is like sufficiently close to the one that we in the ideal setting, but not exactly the same. So again, you let the hidden node interact with the visible node, and now you get a noisy probability distribution. Of course, the noisy probability distribution will be different from the true probability distribution, and the error can be quantified in the following way. So the most general thing we can do is to apply a stochastic process at every step, and we can model this system as P, which describes the original stochastic matrix, and P tilde as a noisy stochastic matrix. And we can quantify the difference between these two by, let's say, the operator norm between P and P tilde. Let's say that is upper bounded by epsilon. By just using like standard triangle inequalities, you can show that the upper bound on the probability distribution between the two is order n epsilon. And you can convince yourself that this is the best you can do. The simple way to see this is that you just choose the P to be something trivial. It transfers no information between each nodes, but you just like add some errors. So you have some like IID noise at every step. And in this case, you can actually compute the total variation distance between these two probability distributions, and you can see that indeed it scales with n. So for each visible nodes, you'll get the following form of error bound. So at the first time step, you get an error of, let's say, order epsilon. And you go to the second step, and you get an order of like 2 epsilon, and 3 epsilon, and etc. But I would like to emphasize that this error bound is actually not quite tight. And the way you can see this is to think of this from the perspective of these like hidden variables. okay? So from the perspective of the hidden variable, it looks as if that at every single time something like new comes up and you interact with this new thing and you throw out this thing. More specifically, at time t equals 0, this hidden node that's up here is interacting with this like visible node. And at time t equals 2, time t equals 1, basically the hidden node moves to the next position and now it interacts with the first one, second one, and etc. And actually, whatever this interaction is, you can, if you only focus yourself on the hidden variable, then you're basically undergoing some kind of stochastic process. So at time t equals 1, you're applying a stochastic map 1, stochastic map 2, all the way to the stochastic map 5. Now, there is a very well-known phenomena regarding the stability of the stochastic process. So specifically, let P be the transition matrix that describes the stochastic process. And basically, the point is that there's a standard result that shows that the eigenvalues of the stochastic matrix is bounded from above by 1 and in terms of absolute value. If you stick in any probability distribution inside this, you can decompose these things into stationary probability distributions and non-stationary probability distributions. And if at the end of the day, if you apply this matrix many, many times, then you end up getting only the stationary distributions. So let's say you start with some probability distribution U, and now you want to apply the stochastic matrix like k times. Now we want to like understand how close these two things are after we apply this for k times. You can decompose this t. This is some variation formula. You can decompose any t into a sum of some vectors, and the thing is, you can decompose these matrices into the following form. Now, this might look very complicated, but this is some trivial identity that you can easily check. And the important thing to note here is that if you look at the nth term of this decomposition, it has the following form. And what's important is that if you investigate what this term is doing, this part is basically some stochastic matrix that is applied to some probability distribution, and therefore this is some probability distribution. And we don't really care what this probability distribution is. And then we have this p tilde minus p. I remember p was the original stochastic matrix, and p tilde was the noisy version of this. So in some sense, the norm of these thing is like bounded by like epsilon. And lastly, we have these individual terms, which is a decomposition of arbitrary operator in terms of like a complete set of eigenbases of p. And we have these eigenvalues whose absolute value is guaranteed to be like smaller or equal to 1. So you can see that when n is large, basically if there is a gap between the largest eigenvalue and the second largest eigenvalue, only the largest eigenvalue will survive, and everything else will be killed off in the large n limit. Okay, so we have this cartoonish picture on what happens to the ith term of this like summation. So at first you have some like order epsilon thing here, but eventually this decays exponentially as n goes to something large. So the sum of all the contributions can be thought as like the area of this curve, and this thing is like epsilon, so the entire thing will be like order epsilon, independent of n. Yeah. More precisely, you have this constant prefactor, which is like 1 over 1 minus lambda 2, where lambda 2 is the second largest eigenvalue of the p. And again, here's like a cartoonish picture. So like if you have like an error rate of these numbers, then if you look at the single local expectation values of this like classical stochastic map, then the error will initially increase, obviously, but then like it will just like saturate at some point. So you might see this like weird curve of like going up and down. This is because like I just plotted the expectation value of a single observable. This would have shown a more monotonic behavior if I computed like the total variation distance of a single site. So from the perspective of the hidden variable, the picture looks like this. So at every time you apply some stochastic map, and by the stability of the stochastic map, the error that you accumulate stays at some like constant level, as opposed to like growing with the number of time steps. So the error scales is like order epsilon, all the way. So now I need to like translate back to the perspective of the visible variables. And now remember the visible variables interacts only like once with the hidden variable. So if the error rate here is like epsilon, you go to the next step and the error rate is again epsilon, and the same thing holds all the way. Okay. So the key insight is that in the presence of the eigenvalue gap of this transition matrix, the error for these like marginal distributions does not grow with n, even in the worst case, which will be this guy. But the error for the global probability distribution will still scale with n in general. So there is this distinction between what's the error rate for the local marginal distributions and what's the error for the total distribution. And the insight to the quantum case is really simple, actually. So we have this like nice formalism about like quantum channels. So you basically, and also, okay, so in quantum case, instead of like probability distribution, you have density matrix. And instead of like stochastic matrices, you have just quantum channels. And you replace everything, and the exact same picture still holds. And of course, like a version of this picture has been studied like a long time ago in the name of like Markovian like co-cycle by Cardi and Frigio. And there's this like very nice paper by Franz Nattergale and Werner, which nowadays is known as like matrix product state. But these guys actually thought about like a physical process in which there's some like hidden thing that is interacting with the qubits, like or like qubits sequentially. Yeah. So there's a nice animation there for you. Yeah. And as I said, you can basically translate everything by replacing the probability vector into density matrix and the stochastic matrix into some CPTP map. And just to draw a parallel between the classical case and the quantum case, I would like to use this notation wherein instead of using like a trace of like rho of A to compute the expectation value, I just consider this vector space in which I have like a space of observables, and its dual space is a space of density matrices. Okay. Now you'll see that the pattern is basically the same. So we can, again, characterize the noise by the difference between the ideal channel that you want to apply at every step and the actual noisy channel that you apply in the experiment. And let's say that is upper bounded by epsilon. Of course, the most general thing you can do is to apply the stochastic process at every step. And so we have like rho, which is the global state when we don't get any noise, and rho tilde, which is the global state when we do have noise. Again, because for the classical case, we already seen that the total distance will, in general, scale with n. This will be the best we can do, order n epsilon. But now we know better. So depending on the problem that you want to solve, maybe the trace distance between two density matrices maybe not the right figure of merit to consider. So again, how do you see that? You have this physical process wherein naively you would expect there is this hidden node which interacts with the visible qubits now sequentially, and you might be worried that if you go all the way to the nth qubit, you get in like error bound like order n epsilon, and that won't be good if n is very large. But of course, from the perspective of the hidden quantum state, you get this picture wherein the hidden qubit just interacts with the new qubit every single time, and that newly introduced qubit is discarded. And of course, all of this process, the channel that is applied to the hidden qubit and the visible qubit, and the act of like tracing out the visible qubit at every step, these are all just some CPTP map. because these are like valid quantum mechanical operations. And there's a very close parallel between the stability of the stochastic matrices and the stability of like a quantum dissipative systems. So basically here what you would do is that instead of like P and P tilde, you have like phi and phi tilde, and you just consider the dual of them to see like how they act on the observables. And there will always be the stationary eigenoperator for these matrices, which will be the identity. And generically, there will be other eigenoperators, and their eigenvalues will be like, in general, not equal to 1. You'll have to like fine tune them to make that happen. So now I can like sort of justify why I use this like weird formula for the total variation distance and in the classical case. So in like a couple of slides before, I had this like formula where in the distance is represented as some like variational formula between rho and this like a t. And this is in quantum information, this is known as Hellstrom theorem. So there is some operator for which you can express the trace distance between these two states by the expectation value of some operator. So of course you can decompose this T into a linear combination of the eigenoperators, which will give you this result. And you can basically just replace phi to p to phi tilde, p to phi, and p tilde to phi tilde. And you can apply the same telescopic decomposition. So again, if you look at the nth term, you have something that looks like this. Looks complicated, but the idea is very simple. So if you look at this thing, this is just some channel that is applied to some quantum state, and therefore this is some density matrix. We don't really care what that thing is. And in the middle, we have this difference between the ideal channel and the noisy channel, and their difference is bounded from above by epsilon, by our assumption. And we have this linear combination of like eigenoperators. So Vi used to be some vectors. Now these are just some operators. And lambda i's are the eigenvalues. So again, assuming that there's a gap between the largest eigenvalue and the second largest eigenvalue, each of these terms, their strengths will scale like this. Again, here we have like order of epsilon, and this thing decays exponentially with n. So again, if you sum over everything, then you get an error, total error that is upper bounded by like order epsilon, as opposed to being order epsilon n. And I should mention that there was this very nice work by Angelo Lucia and Toby Cubitt, Spiros Mikalakis, and David Perez Garcia in 2013. And I didn't use their result like exactly, but like their like underlying logic is general enough that it can be applied to our setting. The only difference is that in their case they have a continuous setting, and in our case we have this like actual discrete time step. But of course, like what I did was to just translate everything that they did into this discrete setup. So after all this, like even in the quantum case, you'll get like an error scaling that will look like this, which will be much better than what you would have naively worried about. So again, from the perspective of the hidden quantum state, you again get this picture. This hidden qubit, or qubit, at every time step is perturbed by like order epsilon, as opposed to being perturbed by order epsilon times t, where t is the number of time steps that you have applied so far. And again, because the marginals interact with the hidden qubit like only once, and because the hidden qubit has like order epsilon error at every time step, for each marginals, you get an error rate of like order epsilon. Good. Now, there are a couple of things that I want to emphasize at this point. So there are a couple of interesting facts, actually. So in the classical hidden Markov process, whenever you have a collapse, this implies that the global state has some like extensive entropy with the system size. So you might be worried that in the quantum case, okay, so you have some sort of like noise robustness, but maybe that's because everything is classical. This is something that you might be thinking, because extensive entropy, it seems like finite temperature, it looks like all the quantumness might have been washed away. But actually there are lots of like pure quantum states for which the gap does vanish, and it does, the underlying state does describe a non-trivial quantum system. A canonical example of this is something called as the AKLT chain, and indeed, in this case, you have you can work out this thing, and you can convince yourself that indeed the quantum operation that you see in this particular state is has a gap. And in some sense, this is possible because such states are entangled. So there's something kind of funny going on here. It's a fact that because the ground states are entangled, but it's not entangled in an arbitrary way, but because they are entangled, you get this non-trivial gap on the CPTP map that is like implicit in this analysis. And because of that, at least for local observables, you get some form of stability. It's kind of a funny thing. But of course, this thing that I described to you, as I said, this is a subclass of the matrix product states for which there is a very efficient classical algorithm to actually simulate that thing. So actually, there's no point in like using a quantum computer to do this. So you have to look for more non-trivial examples. And this is what I did in my solo work in 2017, and also with a joint work with Brian Swingle in 2017. So this is a picture that I tried to draw. You can sort of see that there are these like jiggly lines that I couldn't like just copy and paste. But this is a quantum circuit that is known under the name of MERA. This was introduced by Guy Vidal in 2006, and since then, all sorts of variants and have been discussed in the literature. And this particular circuit is largely inspired by this paper by Evenbly and White, and also Hagemann and his collaborators in 2017. The way you should interpret this circuit is something like this. The time goes from top to the bottom, and these, so this red thing is not a quantum gate. I think this thing has shifted while I was editing the slides. So these big boxes, these are the quantum gates, and these red things are like ancilla qubits, which are prepared in some fixed state, let's say 0 state. So you prepare 0 states and you apply a bunch of these circuits, and at the end of the circuit, you get this many body quantum states, which are supposed to describe some complicated quantum states that people care about. And usually the goal with these kinds of quantum circuits is to compute physical observables of interest. This includes things like total energy, or energy per site, or maybe it's some other order parameter like the total magnetization, maybe whatever you name it. But the point is most of the order parameters that you care about, that you can measure in the experiments, are something that is a linear combination of local observables. So what you do is that in the circuit, you basically remove all but the relevant quantum circuits. So if you go back to this slide, and let's say hypothetically, we want to compute the expectation value of some local observable that is located down here, okay? And then what you would do is that you remove every single quantum gate that would be completely irrelevant for this purpose. A trivial example of that gate would be this thing. So clearly, the gate that is down here, actually anything in this region, has absolutely zero influence on the expectation value of this observable. So you might as well remove them. When you do that, you are left with a picture like this. And although I removed these things rather crudely, you can imagine that, for instance, here there will be some leg that is pointing down, and that qubit, after applying this particular gate, will no longer be used. Okay? And here's where the analogy between the previous picture arises. So in the previous picture, we had this the hidden qubit and the visible qubit. And you can think of this guy as some sort of a hidden, the visible qubit. So there's some a bunch of hidden qubits that are some are smeared inside this thing, and that thing is interacting with the visible qubit down here. And after that, that visible qubit is discarded. We no longer use them. So mathematically, this would amount to like just tracing them out. So you have like visible qubits at this particular time, next time, and all the way. Okay. Yeah. So you get the same picture wherein the hidden qubit interacts with some visible qubits. And what you end up measuring in this particular example is, let's say, the visible qubit at the very last step. So in the things in the middle, they interact, but after that, they just disappear, and we no longer care about it, at least for this particular example. So you get this like dissipated process wherein you have this sequential thing. So what's amazing is that this quantum circuit that I described in this previous slide called that we call as DMERA actually approximates like physical states of interest very well. This was done by a theoretic analysis in Hegman's paper and his collaborators' papers. And the thing is, many interesting physical states actually satisfy this gap condition. And the basic bottom line is that if this gap condition is not satisfied, there will be a correlation that will decay slower than the power law. But in these the states that you are trying to study with these kind of systems, they are usually either at the critical point or away from the critical point. If you're at the critical point, you have like a power law decay correlation. If you're away, you get like exponentially small, exponentially decaying correlation. And either way, it looks like we are safe to assume that this gap condition holds. And there's a sense in which you should expect some form of speed up using a quantum computer. And I will discuss this more on the later slides. So, so you might be thinking, okay, so why? There are a couple of questions that you can ask. So first is that there are these quantum circuits that people propose in the literature. They were supposed to be like efficient classical methods to difficult quantum many-body systems. Why don't we just use a good classical computer to just simulate this thing? The reason is a bit subtle, actually. So if you actually dive deep into this like tensor network literature, you quickly realize that there are lots of polynomial time algorithm that scales with the polynomially with the system size. But actually, it's really, in some sense, the scaling the system size is sort of irrelevant. Like, as Ryan said in the first talk, whenever you have this like many-body system, like all you care about is in some sense like the total, like the energy per site, something that is normalized by the system volume. And when you try to make that precision as high as possible, usually the scaling in terms of this, let's say the error per site becomes not so good. So there are like polynomial time algorithms. But sometimes the exponent in this polynomial is not great. It's something like 1/epsilon to the 9, and that's kind of problematic because like here's one example. So let's say your target error rate is for each local observable is like 10 to minus 3, which is actually like a reasonable number that is like frequently coded in like these tensor network or numerical experiment literatures. And let's say if your exponent is 5, then at least in this particular method, by the way, the exponent is much larger than 5, but let's say that is hypothetically 5, then we still need to store like 10 to the 15 like complex numbers. That turns out to be roughly like 10 petabytes, and then you have to like process this data. So you can sort of see that practically speaking, there's a lot of difficulty in actually running these algorithms. And the way I would like to put this is that the quantum computer, even a noisy one, can make this a little more practical. Of course, quantum computers are sort of expensive, so like you got to like think about whether there's like a cost, whether this investment is worth your price. But at least for doing at least for demonstrating some sort of improvement over the classical hardware, I think this is a good task. And I think I should mention also that really the important metric here is epsilon, which is the error per site, not the total system size, not the total error. And indeed, if you look at these like literatures on like how to approximate quantum states with product state, which was kind of all the rage like 5 years ago, these like product state approximation of like a complicated quantum state. There are these like algorithms that scales like polynomially in like the system size. But if you look at it, like there's this like subtlety, namely the scaling in epsilon is terrible. So like the naive method to do this is to partition the system into disconnected chunks, which are spanning the most of your system, so that energy per site becomes sufficiently close to the ground state energy per site. But if you do this, you basically have to solve your system in like larger chunks with order like whose volume is like order like 1 over epsilon to the d. And to do that, you need some scaling that is exponential in 1 over epsilon to the d. And that's pretty bad. The way I like to put this is that we basically, the tensor network methods reduce this exponential scaling in 1 over epsilon to something that is like quasi-polynomial or like polynomial, but like not so like practical polynomial. In our method, you can see that it's basically 1 over epsilon square. It's because this is coming from the fact that you need to like sample local expectation values, and so you prepare some quantum state and you measure it, and because it's like a single shot experiment, in order to get like order epsilon accuracy, you need like order 1 over epsilon square like repetitions. So so that's not as great as like linear in epsilon, 1 over epsilon, which you would expect if you can do like quantum phase estimation. But this is something that you would do in like a noisy quantum computer, and you'll still get some useful result out of it. So that's the main selling point. Yeah, and one extra thing is that we need to actually find the tensor network that approximates ground state. Of course, you shouldn't really expect there to be like a magic method that always finds the ground state, because that would be ridiculous. But that would be delegated to the classical optimizer, and hopefully people can work out something, some nice optimizer that is suitable for this task. So there are a couple of interesting observations that I think is sort of interesting. So as I said, there already is a quasi-polynomial time classical algorithm, but I think, and you could certainly argue that this is like efficient in some sense, but in practice, this algorithm is not very practical, and we're trying to use a quantum computer, a noisy one, to get some like a more reasonable polynomial time algorithm. Another comment that I would like to make is that one might think that it is impossible to simulate a large quantum system with a small quantum computer, but I think we should try to push this harder. But because once we prepare, let's say we prepare the quantum state, at the end of the day, what we're going to do is to measure some physical observables of interest. And if that's the case, it looks like for extracting expectation values of local observables, it appears that there's a better shortcut by leveraging these classical methods that people have been developing for many, many years. So maybe we should try to do that. And there are some general remarks, which is that I think there's this shallow quantum circuit rage in the everywhere. I really think that there's some limitation on shallow quantum circuits when it comes down to do something useful. So I think we shouldn't be too afraid of deep quantum circuits, but if you don't do error correction, of course you have to design your circuit properly. And hopefully this work shows you that something non-trivial can be done, even with deep quantum circuits. Okay, and I'd like to end with this note. So we usually think of 3 different ways to fight noise. One is better hardware, better error correction, and above that you have this circuit optimization to reduce the total number of gates. But I think this shows that there's something that is one level above that, which is understandably more specialized, but still non-trivial, and that's noise-resilient quantum circuits. Thank you.
Okay, thanks for that, Isaac. Any questions? Okay, well, I can ask one. So I was going to ask, So you're specifically looking at the mirror systems? I guess this is maybe a similar question to what I've asked before, but have you had any more thoughts about other systems that these techniques might work for? So
there's these like PEPs, projected entangled pair states. You can consider like a unitarized version of this, meaning that, so I should back up maybe. So there's this 1D picture wherein there's this hidden qubit and you interact with the like visible qubits like sequentially. Instead of that, you can imagine having like rows of hidden qubits and rows of visible qubits. And you apply like a finite depth quantum circuit on these rows every time. And this modulus some assumptions will also exhibit some form of noise resilience. So that would be another non-trivial example.
So can I think of that as looking like the mirror, but in 2D, and then with something coming up?
It's more like a matrix product state, but like with a like very specific internal structure.
Okay. Okay, if there are no more questions.
Just trying to ask a simple question, maybe for experimentalists. Which of the actual physical qubit systems fit best to your requirements?
Good.
What would you work with?
So for Mera, I found it very difficult to make the circuit like geometrically local. So probably for that, something like any platform that, so for Mera, any platform for which the non-local gates are easier would be better. This other thing that I told Earl right now, this like PEPS thing, that really only involves like geometrically local gates on like nearly like a quasi 1D architecture. So that's presumably easier for like architectures that are constrained by geometric locality.
Okay, so I'll give you some reminders about lunch in a moment. But before that, can we thank Isaac and all of the other speakers in this session?